All right, today we're diving into something that feels like it's been pulled straight out of a science fiction movie. But believe me, it is happening right now. We're talking about brain-computer interfaces, or BCIs.
I mean, really think about that for a second. What if you could move a cursor on a screen, type out a message, or even control a robotic arm, using nothing but your mind? This isn't just some futuristic daydream. It's the very real promise of a technology that could literally change millions of lives.
So at its core, a BCI is all about creating a direct line of communication, a pathway between the electrical signals in our brain and the digital world. It completely bypasses the body's usual network. And the main goal, for now, is something deeply human: to give back function and independence to people who've lost it due to severe neurological injuries.
Okay, so here's how we're going to break it all down. First, we'll listen in on the brain's own electrical conversation. Then, we'll see how AI is learning to be the ultimate translator. After that, we'll look at how companies like Neuralink are trying to package all this up into a real product. And finally, we're going to tackle the huge ethical questions that this tech forces us all to ask.
So how on earth do you even begin to listen to the brain? Well, our brain cells, our neurons, they communicate using these tiny little electrical pulses. You can think of them as spikes. The very first challenge for any BCI is to eavesdrop on this unbelievably complex symphony of spikes with millions of neurons all playing at once and somehow not get lost in all that noise. It really all starts with listening. So you can see here, a tiny microelectrode gets placed right in there among the neurons. You can think of it like a super sensitive microphone picking up all the electrical chatter from lots of different brain cells at the same time. That raw signal then gets amplified, filtered, and digitized so a computer can even begin to look at it.
But here's the catch, and it's a big one. The raw signal you get isn't some nice, clean message. It's a total mess. It's a jumble. You can see those distinct spikes in there, sure, but they're buried in this sea of background electrical noise from all the other neurons, muscle activity, even the equipment itself. It's like multiple people shouting right next to the microphone all at once.
So to make any sense of that chaos, scientists use a process called spike sorting. The best way to think about it is like being in a super crowded, noisy room and trying to pick out what a few specific people are saying. Special algorithms analyze the unique electrical shape and size of every single spike, kind of like creating a fingerprint, to figure out exactly which neuron it came from. It's how you go from a chaotic roar to hearing individual conversations. Okay, so once we've sorted the spikes and we know which neurons said what, we've hit the next huge challenge. What does it all mean? How do we translate that neural chatter into a clear command, like move the cursor up into the left?
This right here is where artificial intelligence comes into the picture. A decoder is basically a really sophisticated algorithm that learns the relationship between patterns of neurons firing and what a person is actually trying to do. It is the digital translator that converts the language of the brain into the language of machines.
And, these digital translators have gotten so much better over time. For years, the gold standard was this linear algorithm called the Kalman filter. But here's the thing, the brain isn't linear, it's complicated, it's messy. So now new research shows that advanced AI models like LSTM, recurrent neural networks, are way better at learning these complex patterns. They can actually understand the context and the history of the signals, not just the one spike happening right now. And that leads to this huge jump in both speed and accuracy, getting users so much closer to natural fluid control.
So how does all this incredible science get turned into a real device that someone can actually use? Well, there's probably no company that has captured the public's imagination on this more than Neuralink. So let's take a look at how they're trying to put all these pieces together.
I mean, if you look at their own white paper, Neuralink's mission is to get this technology out of the lab. Their goal is to create a high-bandwidth system, one that can read a ton of data from the brain and make it scalable. That means it can be used for all sorts of clinical needs, from helping with paralysis to maybe one day even addressing other neurological disorders.
And their approach has some seriously cool innovations. They've developed these super thin, flexible threads for the electrodes, which are designed to minimize any damage to the brain. Their device uses thousands of these electrodes to capture a massive amount of data. They've even built a special surgical robot to do the implantation with incredible precision. And maybe most importantly, the whole thing is designed to be fully implanted, totally invisible from the outside, and it can transmit data and even charge wirelessly. Elon Musk actually described the concept with this really simple analogy. Now, obviously, it's way more complex than that, but the idea is to create a device that just seamlessly becomes part of a person's life, a powerful neural interface that you don't even have to see or think about once it's in. Now, this kind of power, the power to directly link a human mind to a machine, it doesn't just come with technical challenges. It brings us to a massive ethical crossroads, and it forces us to ask some really fundamental questions about what it means to be human and what kind of future we're trying to build here. And we have to tackle these issues head-on. I mean, who owns your brain data, especially if it's being collected 24/7 by a high-tech device? How do we protect our most private thoughts from being hacked? What happens to society if this tech moves from just therapy to actual enhancement, and only the super rich can afford it? And what if a BCI-controlled device makes a mistake and hurts someone? Who's to blame? The user, the AI, or the company that built it? And while all those concerns are huge, neuroethicists point to an even more delicate, even more challenging dilemma: using invasive BCIs in children with severe disabilities who, up until now, have been kept out of these clinical trials. And this brings up its own unique set of problems. You see, a child can agree to something, they can give assent, but they can't give legal consent. And think about this. The success of a BCI depends on months of really focused training sessions. Can we really expect a child to maintain that level of attention? But the most important question comes down to this. Are the massive risks of an experimental brain surgery on a developing brain justified when the benefits are still mostly just seen in a lab?
The general feeling among experts is pretty clear on this. The whole ethical equation changes once the technology gets better. The real turning point will probably be when we have these fully implanted, wireless systems that can be used long-term at home, not just in a lab. Only then might the potential benefits to a child's life really start to outweigh those huge risks. And so, that leaves us right here with this one massive, powerful question. BCIs hold this incredible promise to restore, to heal, and maybe one day even to enhance us. But as we take these first amazing steps toward merging our minds with machines, our biggest challenge will be to navigate this new world with wisdom, with foresight, and with a deep, deep respect for the very thing that makes us human.